Hello students, welcome back to a new class of Thermodynamics. I am Dr. Mohammad Uzair and today I am going to continue the topic of entropy. In the last class, I discussed about the Cauchy's inequality, then I defined the term entropy, and after that there was a concept of entropy change. Today I am going to start with the subheading of the increase of entropy principle. In order to understand the concept of increase of entropy principle, consider we have a cycle. You can see here we have a cycle where we have a process 1 to 2 and we have another process 2 to 1. The process 1 to 2 is basically a reversible or irreversible process, while the process from 2 to 1 is internally reversible process. So this whole cycle comprises at least one internally reversible process. From the definition of Cauchy's inequality, we can say that the cyclic integral of delta q upon t is less than or equal to 0. So this is for cyclic integral. Right now in this cycle there are two different processes. So if I am going to write down the equation for each process, so I can expand like this one. So we have the integral from 1 to 2 of delta q upon t. This is for this process, the first one, 1 to 2, which is reversible or irreversible. And then we have the integral of delta q upon t for internally reversible cycle. And the summation of these two integral is less than or equal to 0 according to the Cauchy's inequality. In the last class, we have already checked that this term, this one, the integral of delta q upon t for the internally reversible cycle is equal to the entropy change. So we know this one is the entropy change, and I can write the entropy change like S1 minus S2. So this is the entropy at point number 1 minus the entropy at point 2. Therefore, I can simply rearrange the equation, so it will be like this one. So we have the integral of delta q upon t for the process 1 to 2. This is for the process 1, which is reversible or irreversible, and then we have this one, which is S1 minus S2, and this is the entropy change for internally reversible process. And as per Cauchy's inequality, we have the summation which is less than or equal to 0. I can replace this one like this one. So I am going to shift this one on the other side, so it will become like this one. And I'm just going to rearrange it because this is S1 minus S2. So if I'm going to shift this one on the other side, it will be S2 minus S1, and then it will become greater than this one. So we have S2 minus S1, which is equal or greater than the integral of delta q upon t. Now we can write this equation in terms of differential form. And when we have to write this equation in differential form, it will become like this one. I'm just going to change this S2 minus S1 and I'm just replacing it by ds. So simply ds is greater than or equal to the delta q upon t. So this is in terms of differential form. So here this symbol shows that either we have the internally reversible process or we have irreversible process. If we are getting the equality here, if we have that ds equal to dq upon t, so it means we will have an internally reversible process. And if there is inequality, so it means we have irreversible process. So I'm just going to examine this equation again. So here we may conclude from these equations that the entropy change of a closed system during an irreversible process is greater than the integral of delta Q upon T evaluated for that process. So you can see here this entropy change is greater than this integral, even here. So this entropy change is greater than the integral of delta Q upon T. And in the limiting case, if we have the reversible process, let's say if we have the internally reversible process, then these two quantities become equal. So here, this equal sign will hold when we have internally reversible process, and it will be unequal, or the entropy change will be greater for irreversible process. So first one is for, if we have the equal one, so it will be for internally reversible, and if we have inequality, then it will be for a reversible process. So remember, probably I just made a mistake here when I'm going to explain this one. Basically, this one is equal when we will have internally reversible process, and this inequality will hold when we will have irreversible process. So remember, in the previous equation, the T is basically the temperature, but it is the thermodynamic temperature at the boundary. While the differential heat, this delta Q is the transfer, is the amount of heat transfer between the system and surrounding. Now, if I'm going to move further, so here this S2 minus S1 is equal to delta S, or the change in the entropy. So this is the change in entropy, and this is only for internally reversible process. For reversible process, it becomes equal to the integral of delta Q upon T, which represents the entropy transfer with heat. So this one is the entropy transfer with heat. As we already seen that there is inequality sign. So it's been the inequality sign in the preceding relations is a constant reminder that the entropy change, the delta S of a closed system during an irreversible process is always greater than the entropy transfer. So this one is the entropy transfer, while we have this one, which is the entropy change. So this entropy change is always greater than this one, or equal to this entropy transfer. But normally in the real life we will not get the ideal internally reversible process. So in most of the cases the entropy change will be greater than the entropy transfer. So that is, some entropy is generated or created during an irreversible process, because we have seen here that we have an unequal sign here. So it means this is the entropy generation, this one, sorry, the entropy difference, and this one is the entropy transfer due to heat. So if I have to make this one, if I have to use an equal sign here, so it means I have to add something here. For irreversible process, I have to add something here with this term. So you can see here that is some entropy is generated or created during an irreversible process, and this generation is due entirely to the presence of irreversibilities. So whenever we have the irreversibilities, then we have to shift, or if I have to make this one equal, then I have to add something, and this addition is called the entropy generation. So the entropy generated during a process is called the entropy generation, and it is denoted by Sgen. So this one, this entropy generation, just to make this this sign of equal here. So in order to hold the equality between the entropy change and the entropy transfer by heat, we have to add an entropy generation term here. So remember, the entropy generation is always a positive quantity or zero. If we have the entirely reversible process, then this will be a zero value, and when we have the irreversible process, then the entropy generation will have a positive value. It can't be a negative one. Since the entropy generation is basically dependent on the process. If we have the reversible process or if we have the irreversible process, we will get the different value of entropy generation. And because it is dependent on the process rather than so it means it is not a property of a system. So in the absence of any entropy transfer, which is the integral of delta Q upon T, the entropy change of a system is equal to the entropy generation. Let's suppose we have an isolated system, or simply we have the adiabatic closed system. For adiabatic closed system, there is no heat transfer, so it means the delta Q upon T term is zero. So the entropy change of an isolated system is always greater than or equal to zero. So if you can see here, the entropy change of an isolated system is always greater than or equal to zero. As we know, there is no an ideal isolated system. So let's suppose if we're talking about the Earth or world, so the entropy is always going to increase or it will remain constant, but it is not going to decrease. So this equation, this equation can be expressed as the entropy of an isolated system during a process always increases, or in the limiting case of a reversible process remains constant. So it's either constant because it's a change with delta S. So if this is 0, so S1 is equal to S2, or it's going to increase. So in other words, it never decreases. So entropy change never decreases. So this is known as the increase of entropy principle. So this equation is basically like this equation is going to represent the concept of increase of entropy principle. Now as we know that the entropy is an extensive property, so it's mean if we in any system, if we have different parts or different processes, then the total entropy of the system is equal to the sum of the entropies of the parts of the system. Let's say if we have a different system, or if we have a different subsystem or different processes here, so the total energy of this system will be the summation of the entropies of all the systems. So you can see here is the summation of all the parts or the processes. And remember, there is no reversible process in actual life. In actual life, you will find that all the processes are irreversible process. Means there is irreversibilities in the actual processes. So it's mean the entropy is going to generate during a process. So if there is entropy generation in the process, so more the irreversible a process, the larger the entropy generated during that process. So entropy generation is basically dependent on the irreversibilities present in the process. If we have more irreversibilities, then we will get higher amount of entropy generation. And remember, for the reversible process, there is no entropy generation, but we don't have the ideal reversible process in life. So the increase of entropy principle doesn't imply that the entropy of a system cannot decrease. This is about the entropy. It's not about the entropy generation. Entropy generation is either 0 or greater than 0. The entropy change of a system can be a negative during a process, but the entropy generation cannot. So remember, entropy change is different thing and entropy generation is different thing. In a process, entropy generation is either 0 or a positive or will have a positive value, but the entropy change can be a negative one as well. So the increase of entropy principle can be summarized as follows. So you can see here the entropy generation If we are getting the value of entropy generation greater than 0, so it means we have the irreversible process. If it is equal to 0, so we have the reversible process, and in any case, if we have the entropy generation less than 0, or we have the negative value for the entropy generation, so it is basically impossible process. So you will not see any process in which you will get the entropy generation less than 0. So remember these three conditions. So this is called the increase of entropy principle. Now here we have a numerical for you. You can see here we have a heat source at 800 Kelvin. So this 800 Kelvin heat source is going to lose 2000 kilojoule of heat to a sink at 500 Kelvin. The sink is basically at 500 Kelvin, and in second part you have to maintain the sink at 750 Kelvin. Now determine which heat transfer process is more irreversible. So we have to check the irreversibilities in this one. So how you can check either the process is less irreversible or more irreversible? So it's easy to check the entropy generation. So I'm going to check these two cases separately. So first of all, if I'm just checking the case number 1, where we have the heat source at 800 Kelvin and the sink is at 500 Kelvin. So it will be like the entropy change of the source, and then we will have the entropy change of the sink. So it will be like this one. So we have the entropy change of the source, so it's simply Q upon T. And here you can see it's like a 2000 kilojoule of the heat is going to lose from the source. So we are going to get we are going to use the negative sign here. So minus of 2000 kilojoule divided by the 800 Kelvin for source. So you will get the entropy change of minus 2.5. So you can see here this is entropy change, and you can get the negative value. For the entropy change, we will get the negative value. There is no issue. But the entropy generation should be a positive or equal to 0. While in this case, the sink is receiving the amount of heat which is 2000 joule. So if I'm going to check the entropy generation, the entropy change of the sink, so it will be Q upon P. So here the sink is going to receive the amount of heat. So that's why we are going to use the positive one here. So 2000 kilojoule divided by 500 Kelvin, because the temperature is 500 Kelvin for the sink. So at the end you will get 4 kilojoule per Kelvin. So the entropy is going to decrease for the source, while the entropy change for the sink is positive one. So what about the entropy generation? So entropy generation is simply the total entropy. The entropy of source plus entropy of sink. So it's simply the entropy change of the source and the entropy change of the sink. So if you're going to add these two, you will get a positive of 1.5 kJ per Kelvin. So this is the entropy generation. So for the first case, you are getting the entropy generation of 1.5 kJ per Kelvin. In the same way, you can solve it for part B as well. So for part B, you are only going to change the temperature of sink, otherwise all the calculations are same. So here I'm going to just represent the final answer. So the delta entropy of the source is the same, which is minus 2.5 kJ per Kelvin, but the entropy change of the sink is in this case is plus 2.7 kJ per Kelvin, because now we are going to use 750 instead of 500 Kelvin. So in this case the entropy generation will be equal to 0.2 kJ per Kelvin. You will just simply add these two entropy change, and then you will get the 0.2 kJ per Kelvin. So here in this case, because the entropy generation is less compared with the previous case, so it means the second case is less irreversible. And you can see here, because there is less temperature difference between source and sink. The source is at 800 Kelvin and the sink is at 750 Kelvin. So if the temperature difference is less, then it will be less irreversible. Otherwise you can compare it with the entropy generation values. So entropy generation value for this case is 0.2, while in the previous case it was around 1.5. So you can see here it's 1.5 here. So the first one is more irreversible, or second one is less irreversible. So the total entropy change for the process in part B is smaller, and therefore it is less irreversible. This is expected since the process in B involves a smaller temperature difference and thus a smaller irreversibilities. So please be careful with the temperature values. If we will have the smaller temperature difference, then you will get the smaller irreversibilities. Moving to the next topic, here we have to discuss about the entropy change of a pure substance. As we already discussed about the pure substance in previous chapters, that we have the pure substance that have the fixed chemical properties. And here in the last class, we were discussing that the entropy is a property, which is the extensive property, and thus the value of entropy of a system is fixed once the state of system is fixed. If it is a property, so it means at the state you will find a property and you will find the value of entropy. So as we know about the state postulate that there is a requirement of two intensive independent properties to fix the state of simple compressible system, and thus the value of entropy as well as the values of other properties at that state. So we can use the entropy value to fix the state of a simple compressible system. Like other properties of a pure substance, we can find the entropy values as well in the given tables. Like we have the tables for saturated water. We have a table of A4 and A5, and even we have A6 as well for superheated table. So from this table you can find the entropy values as well. But the entropy values in the property tables are given relative to an arbitrary reference state. In the steam tables, the entropy of a saturated liquid, which is SF, at 0.01 degree Celsius is basically assigned the value of 0. And then we will have the values relative to this one. So here we are going to solve a question and it will be easy to understand this topic. So here we have a rigid tank which contains 5 kg of refrigerant 134A initially at 20 degrees Celsius and 140 kilopascal. The refrigerant is now cooled while being stirred until the pressure drops to 100 kilopascal. So determine the entropy change of the refrigerant during this process. So initially we have the temperature of 20 degrees Celsius and then we have the pressure of 140 kilopascal. But during the process the pressure is going to drop to 100 kilopascal, and during this one you have to change the entropy change of the refrigerant. So here if you can see in the start we have the state number 1 which is 20 degrees Celsius and 140 kilopascal, and we have the refrigerant 134A. So it means we have to use the table A11, A12 and A13 for refrigerant 134A. I'm just talking with respect to the book that I'm going to follow, which is the Thermodynamics by Sengel and Bowles. So at state number 1 we have the 20 kilopascal and 140 kilopascal, 20 degrees Celsius and 140 kilopascal. So based on this one we can easily check the state, and then with the help of table we can find out the values, which is S1 equal to 1.0624 and we have the V1 is equal to 0.16544 meter cube per kg. I'm going to check the value of volume as well, because it is given that it is a rigid tank. So it means the initial volume and the final volume will be same. There is no change because we have the rigid tank. So we have the V1 which is equal to 0.16544 meter cube per kg. With the help of these two given condition. Now at state number 2 we have 100 kilopascal and we have V2 which is equal to V1 due to this rigid tank. Now with the help of these two given values we can easily check what is Vf and Vg, because this V or this V is basically going to lie in between these two values at 100 kilopascal. So it's mean it will be somewhere in saturated mixture region. You can confirm these answers by yourself. So here you can see the refrigerant is saturated liquid vapor mixture at the final state. Since Vf is less than V2, the V2 is basically V1, and V2 is less than Vg, so it means it's somewhere in the vapor mixture region. So if we have the liquid vapor mixture region, so it means we have to find out the quality, the value of quality, and you can easily find with the help of this formula. You know that the V is Vf plus X Vfg. So by rearranging the equation, I can simply get the quality at step number 2. So it will be simply V2 minus Vf upon Vfg. With the help of given values, you can find that the quality is around 0.859. So it's been around 85.9%. You will get around like 85.9% of vapors, and remaining around 14.1% of liquid R134A. So we have the quality value, and with the help of this one, I am going to find the entropy. So because if you can see here, it's going to ask about the entropy change of the refrigerant during the process. So we know what is S1. So now I'm going to check what is S2. So we know what is X2. So S2 will be SF plus X SFG. So at 100 kilopascal you have to check what is SF. So you can easily check the value of SF at 100 kilopascal, and SFG values is 0.87995. So with the help of this formula, you are going to get what is the S2 value. So S2 value is 0.8278 kJ per kilogram Kelvin. So after knowing the value of S2, we can easily calculate the entropy change. So entropy change will be simply S2 minus S1. But the given S2 and S1 values are basically the specific entropies rather than the entropy. So the total entropy will be equal to S2 minus S1, and then you will multiply with the mass value. So it will be like this one. So entropy change is simply M S2 minus S1. Value of M is given, which is 5, and here you can see I'm going to separate is S2 minus S1. Always remember that you have to separate from the last state to the initial state. So here first state is this one and the second state is this one, so last minus the initial one. Last minus the first one. So S2 minus S1, and just putting the values, you will get the answer of minus 1.173 kJ per Kelvin, and this is basically entropic change. So during this process, the entropy is going to change, and it is basically negative 1. So we will get the minus of 1.173 kJ per Kelvin. This is all about the entropy change of the pure substance. Now if we are going to talk about the isentropic processes, the entropy of a fixed mass can be changed by either heat transfer, because we have the delta Q quantity, or due to irreversibilities. Due to irreversibilities and due to heat transfer, the entropy is going to change. So it means the entropy of a fixed mass doesn't change if we will have the internally reversible and adiabatic system. The internally reversible and adiabatic. For the internally reversible system, we will not have any irreversibilities, and if we have the adiabatic system, so it means there is no heat transfer. So during this process, there will be no entropic change. So normally, if during a process there is if the entropy remains constant, so it is called isentropic process. So isentropic process is where you are going to get the entropic change equal to 0, or S1 is equal to S2. So this is all about the entropic change. So you will not get any entropic change, and it is possible when we have the internally reversible or adiabatic system. So whenever we have the internally reversible and adiabatic system, so it's always isentropic process. So internally reversible and adiabatic system is always isentropic process. But remember that the isentropic process is not always adiabatic and the internally reversible. Now, managing systems or devices such as pump, turbines, nozzles, even diffuser as well, they are essentially adiabatic. Normally, we make sure that there is no heat transfer from these devices, and they perform best when the irreversibilities such as friction associated with the process are minimized. So For these cases, if the irreversibilities are low and they are adiabatic, then they will perform better. Therefore, an isentropic process can serve as an appropriate model for actual processes. Isentropic process is where we don't have any irreversibility, so it's mean in the case of isentropic process, you are going to get the ideal system. So if we have the isentropic process, so it will be treated as an ideal system. So you can easily compare that ideal system with the actual one. That's why the isentropic processes enable us to define the efficiencies for the processes to compare the actual performance of these devices to the performance under idealized condition. Idealized condition because the isentropic processes are always ideal process because there is no irreversibilities and it is an adiabatic process. So here if you can see we have a question for you. We already solved this type of question in chapter 5. We have a steam turbine here. So steam enters an adiabatic turbine. It's known as it is an adiabatic turbine, so there is no heat transfer. There is no heat going in or going out from the system. So we have a turbine at 5 megapascal and 450 degrees Celsius. So initial condition is given or the condition at the inlet is given and leaves at a pressure of 1.4 megapascal. Now, determine the work output of the turbine per unit mass of the steam if the process is reversible. So we have the reversible system and we have the adiabatic system. So it's mean the system is isentropic process. And in most of the cases, if it is not given, then still we are going to assume that the turbines are running at the running with the isentropic process. But in the real one, if we have the real case, then the entropy will change from inlet to outlet. So here, because it is given as we have the reversible process, it is given that it is adiabatic, so it means it is an isentropic process. And during isentropic process, the entropy here at the inlet and the entropy at the outlet will be same. So remember, for isentropic process, the entropy will remain constant. So we have the P1 and T1. So with the help of P1 and T1, and because we have the steam, so we are going to use the steam table, table A4, A5, and A6. So here, with the help of this one, I'm going to find the values of S1 and either U1 or H1. But here, because we have the open system and we have already studied in chapter number 5 that we need the enthalpy value here. So if I'm going to apply the energy balance on this open system, so it will be simply A in minus E out in the form of rate equal to delta E system. So d upon dt of the E system. And now because it is a steady state system, and in the steady state system you will not get any change in the energy of the system. So I can easily say that this one is 0. So energy in must be equal to the energy out. So you will not get any storage or the change in the energy of the system. So energy in must be equal to energy out. So it means the energy which is coming in, it should be equal to the energy that is going out, and we have the output here as well in the form of work, because turbine is always going to produce some work. So if I'm going to write the equation, so we have the energy in equal to energy out. So on the inside we have m dot h1, we have the energy associated with the flow which is coming inside the system. So we have m dot h1, and then we have at the outlet we have the work out, and we have the energy out with this flow that is going out. So we have the m dot h2. We are considering that there is no Q because it's already given that it's adiabatic. The kinetic and potential energies are 0 because it is a stationary system. So if I'm going to rearrange it, so I'll get W dot out is equal to M dot H1 minus H2. The mass flow rate is not given, so I can simply divide both sides by M dot. So I'll get the specific one here. So it will be specific work output, and it will be equal to H1 minus H2. I'll show you in the next slide that what I'm saying. So it will be simply specific output is simply H1 minus H2. So now I have to check what is H1 and H2. So at state number 1, I know what is the pressure and I know what is the temperature. So with the help of this one, I can easily find out the value of H1 and S1. So at state of 1, where we have the pressure of 5 megapascal and temperature of 450 degree Celsius. With the help of this one, and then going to use the steam table, I can easily find out the value of H1 and S1. At point number 2, or at state number 2, we only have the pressure. But due to the isentropic process, we know the entropy of the state 1 and entropy of the state 2 are same. So it's mean at state 2 we have P2, which is equal to 1.4 megapascal, and we have the S2, which is equal to S1, and we know what is the S1 value. So with the help of this one, P2 and S2, we can easily find out the H2 value. So we now have the H2 and we have the H1 value. So with the help of this equation, this is the energy equation or the steady flow energy equation, you can easily find out the work output per unit mass. So you can see here, this is work output and it's simply H1 minus H2. So we know what is H1 and we know what is H2. So just you have to put the values and you will get the answer of 349.8 kJ per kilogram. So this is the work output, and this is in terms of specific one. After this one, we have to study two most important relationships, and these relationships are basically called the TDS relations. TDS, the temperature and property relations, and these are very important relations when we are talking about the entropy. Basically, when we are going to talk about the differential form of the conservation of the energy equation for a closed system, so I can write that we have a delta Q and then we have the delta W equal to the change in the entire energy. And these are due to the path function, and this is due to the point function. So I can write the differential form of the conservation of energy like this one for a closed stationary system. And we are assuming that there is simply compressible substance. Simply compressible system. If we have the simply compressible substance, then we will get only boundary work. Because in the simply compressible system, we don't have any electric or magnetic or any other type of work. So we will have only boundary work. So this is our equation number 1. But from the definition of entropy, we know that if we are talking about the internal reversible, then delta Q upon T is equal to the change in entropy. So I can simply say that the delta Q is equal to TDS. So I'm just multiplying the temperature with TDS, or I'm just going to multiply the temperature on both sides. So T upon T, so it will cancel out. So we get the delta Q is equal to TDS. And for the boundary work, we have the change in the work. For internal reversible, it's only PdV, the pressure times the dV. So if I have to check the work, so I have to integrate it. So from here, from this on these two lines, remember that the area under the curve on a PV diagram is equal to void done, while the area under the curve on temperature and entropy diagram, TS diagram, is always equal to the amount of heat. So if we have the delta Q is equal to TDS and we have the delta W is equal to PdV, so I can easily replace this one here. So I can say that this is TDS, and then we have the delta U, and then, sorry for the interruption from outside. So we have the TDS. Instead of delta Q, I'm just going to write the TDS, and then I'm saying that this is PdV, and then we have the DU here. So I'm just going to shift this PdV on the other side, so I'll get that TDS is equal to DU plus PdV. So we have the temperature times the change in the entropy, and then we have the entire energy change, and then we have the PdV term. So this is the TDS is equal to DU, the change in the entropy plus PdV. Or in terms of a specific one, I can write like this one. So we have TDS, this is the capital S, and then we have here, we have the small letter, in terms of small letters of the specific one. So here, this equation is basically known as the Gibbs equation or the first TDS equation. So we have the TDS equation like this one. So this is the TDS equation where we have TDS is equal to DU plus PdV. So this is the first equation. Since we know that the H equal to U plus PV, by definition we have the H is equal to U plus PV. This is the definition of enthalpy. So if I'm going to replace this one, where is the delta H? if I'm going to replace this du by delta H, so it will be like, sorry, so if I'm going to change the delta H here, if I'm going to differentiate this one, so it will be like delta H or dH is equal to du for this one, and then we have the pv, so I'll get p dv plus v dp. This is the like if you're going to differentiate these two terms, you will get like this one, p dv plus v dp. So this du plus p dv, I'm just going to replace this one, so it will be like dH minus v dp. So if I'm going to shift this one vdp on the other side, so it will be du plus p dv, and it will be equal to dH minus v dp. So it's mean I can simply rearrange, and then I can write that TdS is equal to dH minus v dp. So here we have TdS is equal to du plus p dv. So this is p dv, and here we have TdS is equal to dH minus v dp. So we have the second equation here. So we have two TdS equations, and with the help of this TdS equation, we can even write like this one. That from the first one, we can say that ds is du by t plus p dv upon t, and from this one, if I'm going to divide by t here, so it's simply ds equal to dH upon t minus v dp, like this one. So we have ds du by t plus p dv upon t, and then we have like this one. So we have ds dH upon t minus v dp upon t. So here you can remember it in these terms, in this way, or you have to remember this equation. So it's up to you that you're going to remember in this way or in this way. It's up to you. So here I'm going to finish this class. In the next class, we will discuss about the entropy change of liquid, gases, and solids. So for any queries, you can contact me. Thank you.